Okay, in section 19, we're starting to look at exponential functions, and we are trying to, and the problems that I assigned in 10.2, we're trying to solve these. And so you're thinking about what power do I raise 3 to get 1 over 27? All right, now in a little bit we're going to be talking about logarithms, and there'll be a way to rewrite this and think about it. But if you think about it, isn't 3 cubed 27, right? Well, how could I get 1 over 27 from that? I could say, well, that would be a number on top, and 27 would be your fraction. So let's do the same thing over here. So what power would you raise 3 to? Do you remember that if it's on the terms on the bottom, you could move it to the top and make it 3 to the minus 3? We could raise 3 to the minus 3 power and get 1 over 27. And so that's actually what our answer is the negative 3. 3 raised to the negative third power would give us 1 over 27. So like I said, there's going to be a way to think about this, but this is actually kind of setting us up for the thinking we're actually going to do on logarithms. So this is where we're going with this stuff is logarithms. Let's try another one. Let's try 21. On 21, we get 8 to the 2 plus x is equal to 2. Okay, so how can we look at this? First of all, we've got this 8 here, and it's like a base, and it's got some exponents on it. Now, one thing that you can do is look at this number and then look at 2. Is there a way, if you think about 2, 2 is just a prime number. And if you think about it, you could even write it as 2 to the first power, couldn't you? Is there a way to write 8 in terms of 2? We know that 8 is to the 2 plus x power, but is there another way to write 8 in terms of 2 with a base of 2? What if you had 2 to the third power? Isn't that the same thing as 8? 2 times 2 times 2 is 8. So we could do that, okay? Now if you look, you've got the same base here. You've got a 2 and a 2. What are you going to do about this this power to a power up here? Well, if you remember, you can multiply it. So that could become 2, and then you remember when you have a power to power, you can multiply it, so you could say 3 times 2 is 6, and 3 times x is 3x. And then we have 2 to the first power. Now, if I have two expressions and they have the same base, and they're both raised to an exponent and they're equal, that must mean the exponents are equal. So what I can do to solve for x here is take that 6 plus 3x and set it equal to 1. Okay? So now we can solve for x. This is just an equation we've known how to solve since 7th grade. We can say, okay, subtract 6 from both sides. And you get 3x is negative 5. And if you solving for x now, we divide both sides by 3. We get x is negative 5/3. So our answer is this negative 5/3 here. So again, another strategy is to try to write what's on the left and what's on the right in terms of the same base. Base 2 in this case. Now 23 is a lot like 21. If you look at both sides, first of all, you notice on the left side you've got a number raised to an exponent, and then the one on the right side doesn't look like it has an exponent, but we could put a 1 on it. Now let's look at these bases here. You have a 3 here, and you have a 27 here. Is there any way to rewrite 27 in terms of 3 since 3 is a smaller number? Yes. Okay, let me go ahead and write. We're going to rewrite 27. I'm going to go ahead and put the exponent that was already up here there. Okay, and I'm just going to leave everything else the same, but I'm going to rewrite 27. Isn't that 3 cubed? Okay. Well, if that's 3 cubed, I can use my rules of exponents. I have a power raised to a power, so I could multiply those together. Okay. I can't really get anywhere if I can't get them written down in terms of the same base. Okay. So that's 3. Okay, 3 times 2x would be 6x, and 3 times minus 1 is negative 3. All right, we've got two expressions that are equal to each other. They both have the same base. Therefore, the exponents must be equal. That means that what I can do is I can set this exponent equal to this exponent. So let's go do that. That's how we're going to find out what x is. If I add 3 to both sides, I get 6x is 4, and then I can divide both sides by 6. I can get x is 2/3 if I just reduce 4 6, and so there's my answer for 23. All All right, again, 25 is going to work just like 21 and 23. You could actually do something. You could write, if you look at 4 and 16, you notice you've got two bases and they're both raised to exponents. We cannot solve this if we cannot get the same base there. I could change both of them to 2 and rewrite 4 as 2 squared and 16 as 2 to the 4th, but maybe, since 16 is 4 squared, why don't I just leave the 4 alone? That would be another way to do it. And I could say, okay, on the right, I have an exponent of x plus 1, but I'm going to rewrite my 16 as 4 squared so that they're going to have the same base. That will work, okay? So I have 4 to the 2x plus 5 is equal to 4 to the 2 times x plus 1, because again we have a power to a power, so we're going to multiply those exponents. So we get 4 2x plus 5 is equal to 4, and then you distribute 2x plus 2. Okay. Now, I don't know if y'all have noticed it, there's a little bit of a problem here. If these two expressions are equal, then these two exponents must be equal since they have equal bases. So let's go off and try to solve this. 2x plus 5 equal 2x plus 1. We're looking for an x that will make this work. Okay, so let's start trying to solve. You notice we got 2x on both sides? That's kind of a problem. Let's just decide we're going to move them to the left, okay? So if I subtract 2x from this side, I need to do it to this side. And when I do that, I'm expecting it to cancel out over here, but it also canceled out on the left, didn't it? So what I'm left with was 5 equal 1. That's not true. It's not ever true. What does that mean? It means I have no solution to this problem. So just because somebody writes it doesn't mean it's solvable. Okay, we're supposed to graph these two equations on the same grid. I kind of messed up right in the second one, so I had to scribble it up. The exponent is above the scribbles there. Here's how I would do this one. I would pick some good points. Let's just first look at this first equation, y equal 3 to the x, and let's make a table out of it. If I put in like negative, let's try x's of -2, -1, 0, 1, and 2. Those are just good overall ones. 3 to the -2 power, if we plug that in for x, would actually be 1/9. It'd be 1 over 3 squared, which would be 1/9. 3 to the -1 would be a third. It would be 1 over 3 to the first. 3 to the 0 would actually be 1. And 3 to the first power would be 3, and 3 to the second power would be 9. So if we go graph, I'm going to go graph these. I'll turn this off so I'll have plenty of time to finish the ideas here. Okay, so what I did is I graphed the points. It's kind of hard on this, as it's going toward -10 there. It's really kind of hard to get that graphed in there. It's never actually going to touch that x-axis over here. The x-axis is an asymptote. Remember, what an asymptote is it's getting really close to the x-axis over here as it gets very negative, but it's never going to touch. Now, if I do that one by a table of values, and I just did it by hand, but you could even get that off your calculator if you wanted to, I'm going to go graph the other one in green, okay, this 3 to the x minus 2. Now, let's talk about that for a minute. I'm going to rewrite it down here. I could go make a table of values for this also, but there's an easier way to do it. Do you remember how we labeled, every time you saw an x, you could label that x minus h, where h was a horizontal shift. Anytime you see an x, we've seen things like x minus h squared is y minus k or something. We've seen these horizontal shifts earlier in the year. Well, we can do that also with this for exponential equations. It would be y minus k is a times your base, b, which is 3 in this case, and then x minus h, where h is the horizontal shift. Well, if I have x here, there's my x, there's my subtraction sign, my h is equal to 2. That means I have a horizontal shift of positive 2, which means if I just take that graph that I have there and I move it right to, I'll have the graph of my new function. And you can kind of check that out by looking at your calculator and typing both of these in. When you type this in, you'll need to make sure you put this exponent of x minus 2 in parentheses. You can type in 3, and then that exponential thing that looks like a house top, and then in parentheses x minus 2 if you want to type it into your calculator. So if all I got to do is take some good points and move them right to, I could take this one and go 1, 2 over here, so it's going to end up here. This one will be here. I'm just taking good points and moving them right too. Now it's kind of hard because this one at -1 it was supposed to be a third. It's going to be kind of hard to get that in there. And then at -2 it was supposed to be a 9. So it's like almost touching, and I can't even with this stylus draw it where it's going to look like it should really, but you could always look at this on your calculator. It's the same graph, it's just scooted over 2 units to the right. This is why we would call this first function that I circled in red, and I just put a little green on, that is the parent function for exponential equations that have a base of 3. And then if I graph it out to graph the second one, all I'd have to do is take the one that I graphed for the parent function and scoot it to the right too. So remember when we have an x, there's always an h with it. It's usually x minus h. That h is the horizontal shift. Now 35 is going to be a similar thing to 33. It's just a little bit more involved. If I look at this as the parent function of y equal 2 to the x power as the parent function of all exponential equations that have a base of 2, I can pretty easily graph it by making a table of values. And usually we usually pick like -2. Why is this not writing? Negative. We usually plug in x's like this, okay? Those are kind of our standard ones. So if I have 2 to the -2 power, that ends up being 1 over 2 squared, which is a fourth. 2 to the -1 power would be 1 over 2 to the first power, which would be a half. 2 to the 0 power ends up being 1. 2 to the first power ends up being 2, and 2 to the second power ends up being 4. I'm going to cut this off and graph that, and then we'll go discuss the other function. Okay, I put some dots on there. I'm going to try to connect them now. If I wanted another point, I could actually put 3. 2 cubed would be 8, so let me put that one in there. You can see that when I put that one in there, I had kind of gone off to the right a little bit more, so just kind of ignore that little split off to the right there. So now if I want to graph this other one, this is in the form y minus k is 2 to the x minus h power. If you remember, this would tell me I have a horizontal shift of 4, which means I'm going to move everything right 4 for the second equation. But I also have a vertical shift. The k was the vertical shift, and here's your y, here's your minus, so k is 3. K is the vertical shift. I'll just put VS, and that's going to be up 3. So I'm going to take those good dots I graphed and move everything right 4 and up 3, and that will be my new graph for this black equation. I'll graph that in red. Okay, so I've got some good points. What's happening here is it's going to get really close to this line, y equal 3, but it's never going to cross it, and then it's going to start swinging up like the other one does. And see, I didn't have to go plug in a lot of points and get a table and graph everything. All I had to do was graph the first one and then scoot the points right 4 up 3. That's why we like transformations. They're a whole lot easier to graph when we look at them that way. So if you were just told to graph this one over to the left, this harder one that I graphed in red that I'm circling here, I could graph the other one and then just scoot it over and I'd be done. And I wouldn't have to have, really weird values over here where I had to do a whole lot of algebra to find them. And I know you can put those in your graphing calculator, but you need to be able to look at that and see how to do it this way. I mean, if you were stuck on a test, you could do it with a graphing calculator, but I would really discourage you from doing that. That means you're not really understanding the math if you couldn't take this and make it scoot it over like that. A lot of times what I'll ask too is how is this second equation different from the first, and you just have to tell me it was scooted over right 4 and up 3. That's what I tend to do on tests anyway, is not ask you to actually graph it, but just to tell me how it's been changed.